easier later, I guess. so we're gonna just do it, right? It's later in this chapter, but we're gonna just do it now. E to the x. E to the x, the derivative of e to the x is e to the x all day long. Woo! Well, you're gonna get the y later. Just tell me, I'm just letting you know this is true. You're gonna get the y later. I'm getting there. Just wait, I am getting there. So if you have e to the u, because this is now the chain rule, again, I'm going to explain it later why this is true. This is going to be equal to the derivative of u, e to the u. So as an example, if you're trying to find the derivative of e to the 5x, this is going to be the derivative, d dx, of 5x multiplied by e to the 5x. So again, just a leap of faith, only because you need this for your project, this is going to be 5e to the 5x. Just because you need it for your project. We'll go into this deeper later, not right now. All right? I'm going to talk really briefly about another homework question. It was something about, I think there was an x squared involved, and it was something about going through some point, was it 4,15? Is that right?
Oh, yeah.
Oh, yeah. You're all like, yeah, that was like the best question, and please put this on the test. Is that what you all were saying? Okay, so first thing we're going to do is find the slope. We're going to find the slope of the tangent because we need to figure out what point. I think the homework question was something about you need to find the point on the graph so that the tangent line will go through that point 4,15 or something like that, right? That was something similar to that. Okay, so the first thing you want to do is find the derivative of the function because that's going to give you the slope of the tangent. So that's the first thing you're going to do. Do d dx, which is equal to what? 2x. Now we have this equation called the point slope formula that we all forgot. Y is equal to mx, or mx minus x1 plus y1. So we know the slope is 2x. And then we have the point that we are going to use is the point 4,15. So we have x minus 4 plus 15. How are we doing so far? Doing okay? So I'm just going to multiply this through, and I get y is equal to 2x squared minus 8x plus 15. How are we doing so far? Doing okay? Cool. Now, this line, and this is a line. It doesn't look like a line, but it is a line because 2x is a slope. It's an equation of a slope. So this really is a line, even though it doesn't look like it. It looks like a quadratic. I need to know where this line crosses, touches that quadratic. So now what do I do? The big old F word, yes, your factoring friend. So go ahead and move the x to the other side of the equal sign, the x squared, because it is a quadratic. We need to set it equal to 0. So 0 is equal to x squared minus 8x plus 15. And what does this lovely factor into? Because it is lovely. So if you're coming from the left, your x is going to be 3. You have to put 3 into x squared, so your 9 comes out. If you're coming from the right, then it's 5, comma 25. Done.
So we're just replacing y with x squared.
Because you need the curve and the line to touch. You need a point of intersection.
So you're just, okay, so the x squared is just the original function you're saying.
Yes. So do you all remember, you probably don't, but do you all remember in pre-calc 1 where you had to find the systems of equations? We start out with linear systems and then we do nonlinear systems. That's what we're doing. Cool. You're all excited. I can see the excitement on your face. All right, here's where we were yesterday. We can use this here, this formula here to get an approximation. It's not going to give me the exact, it's just an approximation, and there's going to be an error involved with this because it is only approximation. So we're going to use that formula there to figure out the estimate, and then we're actually going to figure out what the true value is. So I have f of 3 is 2, f prime of 3 is 5, and I want to estimate 3.1. So I come back up to this formula, which is f of x plus h. So I'm going to use the formula f of a plus h is approximately equal to f of a plus, oh, I'm going back and forth. This is making myself sick. F prime of a times h. F prime of a times h. Now we're going to use this as an approximation. So I'm going to figure out what my h is. What is my h? So I have information on 3, so f of 3. So what does my h must be? So I'm estimating it for 3.1, but what is my h? How far did I travel between 3 and 3.1? 0.1. So they're asking me to find f of a plus h, which in this case happens to be f of 3 plus that 0.1, or 3.1. Okay? So this is going to be equal to what f of a was. Well, that's f of 3. So f of 3 is 2. So this is going to be equal to f of 3, which is just 2. And then it's going to be plus f prime of 3, and then multiplied by our h, which is 0.1. So plus 3, or 5, multiplied by that 0.1. So this will give me an approximation for 3.1. So what do you all have when you do 2 plus 5 times 0.1? So we have an approximation. This is approximately equal to 2.5. That's it. Any questions before I have you do the second one? Are there any questions at all before I have you do the second one? No? Yes? No? No? Okay. Please do the second one. So on the second one, I have f of 10 plus 0.2 is equal to f of 10. And then it's going to be plus f prime of 10 multiplied by 0.2. So this is going to be equal to negative 5 plus 6 multiplied by 0.2. And what is your final answer? Negative 3.8. How was that? Cool. If we have the function, I can actually tell you what the actual value should be, and then we can find that error, but we don't have the function, so we can't do that. But if we have the function, I just plug in 10.2 with the derivative, and then I compare it to what the estimated value is. Okay, that'd be the error. Go ahead and read this loveliness in all of its glory. The important thing that you get out of this is if you take the derivative of your position, you're going to get velocity. If you take the absolute value of that derivative, then you're going to get speed, because speed does not have a negative attached to it, but velocity could. You take the second derivative of your position, and it gives you the derivative of velocity, which gives you your acceleration. The one that's not on there is jerk, and that is, I can't remember the notation for jerk, but I do know it is the third derivative of your position. So the third derivative of your position, which is the second derivative of your velocity, which is the derivative of your acceleration, and this will give you your jerk. So if you're sitting in one of those god-awful teacup rides where it jerks you around as you get to an end and then it jerks you in a different direction, that force that you feel and before you puke is the jerk. Yep, and instantaneous. All right, some things that you need to know about acceleration and velocity and all that stuff. So I'll stop. So not that I ever speed, because I would never do that. That's not what I do. So in the morning, right, here is your time, and here's my distance from home. So in the morning, I'm at home. I have to wind down a road to get off the hill, so my acceleration and speed is pretty slow. And then I'm on a river road, and people are idiots, so I'm still a little slow. And then I get on the freeway. And then I have to get off the freeway, and then I'm standing stationary because I'm here at school and I'm not moving my car. So my car is standing stationary for some time. And then I get on the freeway, and then I'm still on the freeway, and I'm still on the freeway, and then it starts to clear up. And then I get back home. So that is not the path I traveled to get to and from work. That is my position with respect to time, the distance from home and back. Now, because I came back down to here, that means I came back home. Okay? So this part right here is after you hit Highway 12. Get past Highway 12, then it pretty much cleans up. But anyways, back to this. So when we're talking about the position graph, it is not the path you traveled. It is where is your position with respect to your starting point with respect to time. They're not the same thing typically. Velocity is the derivative, and it is respect to time. Speed is the magnitude of the velocity. That is the absolute value. So when we talk about magnitude, it's the absolute value. Velocity has direction and magnitude. The direction being slowing down or speeding up, whereas speed is just basically I'm going 35 miles an hour up that hill to Highway 12, having a heart attack. Saying, get the factor out of my way, and why the factor are you in this lane? And then I hit Highway 12, and then I get to go the speed limit, give or take. Acceleration with respect to time, acceleration is positive. That means your velocity is increasing. If your acceleration is negative, that means your velocity is decreasing. So as an example, here is a patrol car, and it is a strictly east-west or north-south if you would prefer. And so he leaves his station right here. And the first 30 minutes, he's got a slow acceleration. And then his acceleration looks pretty constant in that area. And then his acceleration slows down because he's going to sit by the freeway and gun you. And now he's waiting here for somebody to get pulled over with his speed gun. And then he sees somebody, he gets back on the freeway, and he's not going to speed much. And then he blows past the station because he's still chasing that car that's not pulling over. Do you like my stories that go with this? Yeah, so do the derivative for acceleration. That's the derivative of velocity, give or take, so do the derivative of acceleration now. So when you're doing the acceleration graph, wherever the velocity has a maximum or a minimum, what's happening to my acceleration graph? I am crossing the x-axis, so I'm going to be crossing about here. I'm going to be crossing about here because that's the position in which I have a maximum or a minima. So in this region from 0 to about 0.75, I am above the x-axis. And then from about 0.75 to 1.5, I am below the x-axis because I'm decreasing in my acceleration. What's the derivative of 0? 0. Still 0 all day long. And then I am, the next part, am I increasing or decreasing? Decreasing. And then what? And then increasing. Okay, so that is the derivative of the velocity, give or take. It may not be that high. It's not perfect. How was that? Is that okay? Cool. Let's take a look at the applications. We have suppose a stone is thrown vertically upwards with a velocity of this. Find the velocity and acceleration functions and determine the intervals in which the stone is slowing down and speeding up. Okay? So go ahead and find the first and second derivatives, and then I'll show you how to find where it's slowing down and or speeding up. So what do you all get for the first derivative, or the velocity? Do you all agree? And then what do you all get for the second derivative? And I expected that. I expected that because we are in feet per second, and that is what acceleration to gravity is 32 feet per second. So I expected that in this case. So they're asking where I'm speeding up and slowing down, so that's in reference to my velocity. So I'm going to set this thing equal to 0. And I'm going to solve for t. So t is going to equal to 2. How is that? What does that represent then? T equals 2. It represents my turning point. It is the position of my turning point. So from 0 to negative 2, I'm increasing. And I know I'm increasing because it's an upside down quadratic. It's a negative, so it's upside down. So my increasing interval, I am going uphill from negative infinity, or negative 0, so not negative infinity, from 0 to 2. And then I'm decreasing from 2 to when I land. How do I figure out where I land? Because obviously it makes no sense to continue to fall. I set my original equation equal to 0 and I solve. So if I want to know where I decrease, I need to go back to my original equation, which is negative 16t squared plus 64t plus 96. And I need to set this equal to 0 to figure out where this thing lands, where my distance, where my position is at 0. So I'm at the ground again. So you can either, if it factors, factor it. If it doesn't, throw it in the quadratic. First thing I would do is look to see if 16 is divisible by all those numbers. Is 16 divisible by all those numbers? Yeah, does negative 16 divide all those numbers?
Yes.
So if negative 16 divides all those numbers, the first thing I'm going to do is work with smaller numbers, even if I throw it in the quadratic. And so I have t squared, and then it's going to be minus 4t, and then it's going to be minus, what is 96 divided by 16? 6 is equal to 0. So does this factor nicely? Give or take. T and t. What does this factor into? What does this factor into? Does this factor nicely? No. Oh, that's unfortunate. So you're going to have to throw this lovely in the quadratic. That's unfortunate, but exciting. We are excited about throwing this into the quadratic. You've never used a quadratic? Oh, of course you're going to have to use it.
Almost gave her a heart attack.
I know, right? You use that forever and ever until you're done with math.
Positive 4 plus or minus.
So t is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And you're going to get a positive and a negative. Does it make any sense to have a negative answer here? That means you're going back into time. So you're going to have to figure out what this is. It's going to be the positive. And I'm running out of time, and I need to get through this section. So let's just talk about the next question. The next question is we have this potato launched. And I want to find the velocity of the potato after 5.5 seconds and 5.75 seconds. My goal in life, by the way, is to do the, do you all know what the pumpkin chunkin is? Chunkin
Oh,
pumpkins?
yeah.
My goal is to someday get a group of students and do that. So I think that would be awesome.
You have your starting group right
I got my
here.
starting
We're
group.
gonna do what?
You need to go on YouTube and look for is it Pumpkin Chunkin'?
Pumpkin chunkin'.
Yeah, Pumpkin Chunkin'.
It's-
It is
It feels
my
very
goal.
American.
It is so very American. It is my goal in life to go there with a group of students.
It's
All right.
watching pumpkins.
So find your first derivative. That's how you're going to do the first one. So find your first derivative and plug those numbers in. I'll give you a moment or two to do that. First thing I'm going to do is find the derivative because it's asking for the velocity. So we're going to find the first derivative because it says velocity. Keyword here is velocity. If they're giving us the position function, then I would need to do the first derivative to find velocity. So s prime of t is going to equal negative 32 t squared plus 100. And I'm going to put in there the 0.5, I'm going to put in there the 5.75 and determine what the velocity is. So to answer the first one, I'm going to do s prime of 0.5 and get an answer. And then s prime of 5.75 and get an answer. Oh yeah, thank you. Sketchy today. So when you put in 0.5, what do you all get out?
84.
Negative 4?
84.
84? When you put in 5.75, what do you all get out? Negative 84? So this answers part A. Part B is the speed. So this is A. B is the speed. So what is the speed? 84. It is strictly just 84 for both of them because speed does not have direction. So the speed, when you're doing the s prime of 0.5, you do the absolute value, which is 84, and then s prime of 5.75, which is still just 84.
They use the same units as feet per second.
Yep, same units.
What unit would it be?
Feet per second. Yep, feet per second. We want to know when the potato reaches its maximum height. How do we find that? We set our derivative equal to 0, so to do the next one, we're just going to set this thing equal to 0 and solve. So I'm going to do the negative 32t plus 100 is equal to 0, and I solve. What is t equal to? Whatever 100 divided by 32 is. 3.125. So after 3.125 seconds, I have reached the maximum height. Oh, 125. Man, I am sketchy today. So after 3.125 seconds, I've reached max height. Define the acceleration. What's the acceleration going to be? It is the second derivative. It is a negative 32 feet per second per second. So on 4 here, this is just the acceleration due to gravity, so it's negative 32 feet per second per second. How long is a potato in the air? How do I find that information? Position equals 0. And I solve. And James, here's your quadratic yet again, possibly. He's like, no, it isn't. Yes, it is. How do I determine the velocity upon hitting the potato when it hits the ground? That's the only one that's new. How do I figure out the velocity when the potato hits the ground?
I mean, synchronous velocity is 0.
All I do is I figure out what the time it takes to hit the ground, and I put that value in my derivative. That's it. So if I want to know what the velocity is when it hits the ground, I have to figure out how long it takes to hit the ground, and I put that value in my first derivative. That's going to tell me my velocity. That's it. Next one, here's our position. We're almost out of time. Here's our position graph moving along a straight line. Sketch your levels of velocity. Do the velocity. Oh, we've done that kind of thing. Let's do this one because they're on there. What does P prime of t represent? If we're doing the bacteria after t days, what does p prime of t represent? It is the rate of change over time, and it could be increasing or it could be decreasing. So this is the rate of change over time. Do I expect it to be increasing or decreasing, and how would I know? So it's increasing because my leading coefficient is positive, and so when I do that derivative, my bacteria is increasing. Okay? What is the rate of the population changing after 1 day? What am I going to do with that information? Just plug it into the derivative. What is the initial population?
That, the original function, but plugging in 1, or plugging in 0.
So when you're ever asked for the initial,
Oh, it's the constant.
it's always the constant. So there's the initial population of the bacteria, excuse me. And then up here, the initial height of your potato is 85 feet. Initial height of your projectile is 96 feet. So that constant is always the initial height, in this case height, or down here, the initial population. How long does it take to double? What do I do to do that one?
You just set the equation equal to the constant squared.
Not squared.
Or times 2.
Times 2. So I just set the original equation equal to the original population times 2. And what is the growth rate when the population doubles?
Do you have your double population solve for t?
After I figure out what my time it takes to double, I just put that back into my first derivative, and that's going to tell me. Okay, so then the last part is this. For those of you who are going into business, the cost, the marginal cost, is the first derivative of the cost. The revenue is always equal to the revenue generated is the number of pieces that you sold multiplied by the price. The profit is the revenue minus the cost. So that's P of X is the revenue minus the cost. The marginal profit is, of course, that first derivative. So here is the cost. If I want to find the marginal cost with that equation, how do I find the marginal cost? Just find the first derivative. If I want to find the marginal cost to estimate the cost of manufacturing the 13th food processor, what am I going to do with that 13th? Number 13, lucky number 13. Plug it into their first derivative. There you go. This section's done and dusted. Enjoy.